In the earlier segment, we talked about many reactions that alkyl halides take part in. Largely, alkyl halides takes part in nucleophilic substitution reactions. In this segment, we will focus on the reaction mechanisms that involve alkyl halides, how it's specific, and we'll be looking out for nucleophilic substitution reaction mechanisms. This is a nucleophilic substitution reaction. The curious question is, how does this substitution reaction take place? We have started out with two reactants, one the bromoethane molecule and the other the hydroxide ion. So it's natural that we would expect the reaction to take place when there are two particles that collide with each other. Now, this collision happens at the same time, so would it be possible that the carbon-halogen bond actually breaks when the hydroxide ions attack it? So it happens something like this: when the hydroxide ion attacks, the carbon-halogen bonds break. The second possibility is to ask ourselves, what happens if only the carbon-halogen single bond break first? Then that gives us a particular structure called an intermediate, and then the hydroxide ion will attack this intermediate to form us the product. Well, the mechanism of the nucleophilic substitution reaction shows us that both possibilities can be possible. This mechanism, we are talking about bimolecular nucleophilic substitution, which is also known as SN2. In this reaction, what happens here is that it follows the principle that both the nucleophile as well as the alkyl halide will collide with each other such that the reaction or the substitution reaction will take place. So we start off with the alkyl halide. In this particular mechanism of SN2, this is a single step reaction. What happens here is the halide ion is a very stable leaving ion. In the idea of the alkyl halides, you have the existence of the carbon-halogen single bond. This carbon-halogen single bond is actually a polar bond which gives carbon a delta plus charge. The carbon-halogen single bond is polar simply because the halogen as well as the carbon has electronegative difference, and that results in the polarization of the bond. Now the carbon with a delta plus is electron deficient in nature and therefore would be able to attract anyone who has a rich source of electrons. A nucleophile is present and the nucleophile has a rich source of electrons. Its rich source of electrons come from the lone pair of electrons which is available, and the lone pair of electrons on the nucleophile is attracted to the carbon which is electron deficient in nature. So the nucleophile is attracted to the carbon which is an electron deficient carbon. What happens here is that the nucleophile will purposely only attack the back of the CX bond. In the mechanism for the nucleophilic substitution, the nucleophile will not attack in any other directions but the back of the CX bond. So what happens here is that when the nucleophile comes closer and closer to the alkyl halides and causing the collision to take place, the CX bonds will start to stretch. Stretch in a manner that the CX bond break with the pair of electrons going towards the halogen. This process of the nucleophile coming towards the alkyl halides and the halogen leaving the alkyl halide results in the formation of a pentavalent transition state. This pentavalent transition state has a negative charge, and the charge of this transition state is dependent on the nucleophile. In this case, we have made use of a nucleophile that is a negatively charged one, hence our transition state is also a negatively charged one. The symbol that is blinking is actually the symbol that represents the transition state. As mentioned, the nucleophile is approaching the alkyl halide. So when the nucleophile is approaching the alkyl halide and going towards the electron deficient carbon, a bond is somehow being formed slowly between the nucleophile and the carbon. This bond that is being formed is represented by the dashed line, which means it's a bond that's on its process to be formed and it is not formed yet. Whereas what happened here is the halogen is leaving the alkyl halide, so it's slowly, the carbon-halogen single bond is slowly being stretched. The slowly being stretched and slow breaking of the carbon-halogen single bond is captured by the dotted line between the carbon as well as the halogen. Now this structure where the nucleophile approaches the alkyl halides and the halogen leaving the alkyl halides, this process forms us the pentavalent transition state. Now if the particles contain sufficient energy to overcome the activation energy, the transition state will move towards the products. So we will have the products that being formed. Do take note that the transition state is actually very difficult to be isolated and it only exists for the short moment. It's not possible to be isolated, not like the reactant, not like the product, not like the intermediate. Now, when we form the organic compound for this particular reaction, we notice there is an inversion. So let's investigate the reactant and the product so that we can clearly see where the inversion happens. Now, let's take a look at the R groups. Now, if you take a look at the R groups, it can help you better to determine that the inversion of the organic compound has happened after the nucleophilic substitution reaction. Let's pay attention to the R group of the reactant. The R group of the reactant is pointing towards the left-hand direction. At the end of the reaction, the R group of the product is actually pointing towards the right-hand direction. If you notice, the R group here is not involved in the chemical reaction. The change in direction from left to right shows that the organic compound has indeed inverted. Now this whole mechanism drawn represents a single step reaction that you need to draw that shows you the mechanism of bimolecular nucleophilic substitution, also known as SN2. This single step reaction is generally favored for primary alkyl halides, in a small degree some amount of secondary alkyl halides. And because it is a bimolecular nucleophilic substitution where both reactants have to collide each other and they will affect the rate of the reaction, the rate equation for an alkyl halide that undergoes a nucleophilic substitution in SN2 mechanism would have the concentration of nucleophile affecting the rate as well as the concentration of alkyl halides affecting the rate. This whole slide demonstrates how nucleophilic substitution reaction happening by SN2 occurs.